Good morning. I was joking with a couple people. It would have been easier if I just did a wrestling WWE entrance here, jumping up on the stage. Yes, Eric Waters from RDH Building Science. I'm definitely excited to be here, both here for this presentation, but also here in Lethbridge. I'm excited to be. We moved here maybe 7 months ago, so excited to dive in. But without further ado, let's dive into. I'm on to the different presentation here. Which one? They were on the same page. The LEEP technical training for net zero energy wall assemblies. To set the preface, I really enjoy building science. I really enjoy building. I get excited. Sometimes when I get excited, I start to talk fast. So if I start talking too fast, just give me a little wave and say, oh, slow down, Eric. Let's pace ourselves here. Let's dive into it. But I'm here. I'm also excited because for this material, the resources we're going to go through, primarily because they're set up to help on every level. Help builders for the construction, help designers kind of put together the pieces, architects, make sure we have the right process included, as well as building officials in the inspection process. Make sure we're all on the same page. So I find it's a very useful document for across the range of the industry. I'll pause for a second to acknowledge Graham Finch and James Higgins. If I wasn't here, and if James hadn't had his third baby, he would probably be here presenting. So congratulations to him, and lucky for me, I get to be here, so I'm excited about that. But these two individuals were part of RDH, and they are key contributors to the technical side of things, as well as developing this resource. So as we go through it, we're gonna thank them a bit for it as well. Now taking a pause to look at what are the objectives of LEEP? What are the objectives of these guides? There's 7 documents. What are they trying to get at? And essentially looking to get a higher performance out of these assemblies, and they do that by building on familiar wall assemblies, conventional things that they're part of the industry, and they do that primarily by increasing the effective R value and reducing that thermal bridging, also by increasing or improving the air tightness of those enclosures, reducing the energy loss, that heat and cooling across the assembly. They also do it by improving the water resiliency of the assemblies, both by managing moisture and vapor, as well as looking at the building as a whole for that redundancy and that durability of the assembly. Drum roll. The 7 documents. So there's a package of 7 to come together. It's available on NRCan website. The first being an intro and wall selection guide. So this is your starting point to look at the 4 different wall assemblies that are going to present in these different guides. And each guide is a standalone document that's a resource by itself. And this one helps select which way to go from there, which type of installation, which type of wall assembly works best for us. That leads us nicely into the 4 wall assemblies. Again, each one of the 4 is a standalone document, 50 pages or so, but each one talks about their wall assembly, has documents supporting that information, details for that assembly, and kind of walks you through that, again, standalone for each one. To support those documents so far, it also has Appendix A, which includes a material selection. So we're going to dive into each one of these documents, but talks about the material selection available to know which ones are more dependable, which ones are more construction grade versus consumer grade, and to be able to know what's reliable for those materials. And then Appendix B, a fun one for sure, is the exterior insulation section. So this talks about, when we look at the 4 wall assemblies, of those assemblies, what insulation types are we talking about? We're going to dive into each one of these documents, and as we go through it, will be time to pause, ask questions, but also if you have questions, let me know. To tease you in case you don't have to look at this later, we also have a QR code up in the corner. I'm sure you can get a thumbs up to make sure it works, but this will take you to the NRCan website, and you can download documents for free and also point others to those documents as well, so they're readily available. We've got some people taking photos, so I'll pause there to make sure we can get access to that. I think we have that QR code at the end of the slide presentation as well, so not to worry. Agenda. We talked about the materials, we talked about the objectives. How are we going to go through this? First, we're going to talk about Enclosure First, why that's important. It's not just because I love enclosures, I think we should be priority. It's because it plays a key role in that building development. So we'll dive into that. Following that, we'll dive into that first document, the wall selection overview. From there, we'll go into each one of the 4 wall guides. Pivoting on that, we're actually going to go to Appendix B first, because it dovetails really well into the rest of the guides. Following that, we'll wrap it up with some material selection, and then we'll have some fun after that, looking at some case studies about how this incorporates not just to new construction, but also existing buildings, retrofits, renovations. So let's dive in. Not your typical house. It's a cheese grater house, not exactly what we want to live in. This is a fun chat GPT rendering of putting in a leaky house. And so my colleague put this slide together. I had some fun looking at this. And one thing it highlights here is that, air tightness of a building is really the accumulation of all the little holes. Here's a little easier to see those holes because it's a cheese grater house, as opposed to our normal construction. It can be hidden behind cladding. It can be a hidden discontinuity, and really that air tightness is something to be addressed. But when we look at this as an enclosure first, net zero energy approach, why is that important? I mean, when we are heating our building or cooling our buildings, the energy gets lost. It exits out those holes. I mean, as a start, we have a mechanical system help keep it cool and help keep it warm. So we'll add a heat pump. But the more air leakage that building is, the harder it is to keep up with it. This can be a slippery slope. Well, it's more air leakage. Let's make a bigger heat pump. From the mechanical side, I'm sure they're all on board with this, which is great. But it's really optimizing that balance, because we can get pretty big, pretty fast. And if we can fine tune those details, especially the air tightness, then we can reduce the need for that. And that's where we can reduce that size. I don't know if they've gone to like a bronze or a golden color of a cheese grater house now, the step up. But the intent here is to improve the air tightness, improve the R value, and then following that, after we kind of optimize that, then the mechanical system can follow and really design that to the load needed as opposed to like a worst case scenario for air leakage. So that air tightness, again, is fundamental. It's fundamental in building science, but it's also fundamental in that net zero energy performance target. And so we look at a wall assembly, take a building, we slice it in half. There's the air barrier, but there's a lot of details to go with that. Every transition, every interface, every new fenestration, that needs to be detailed to make sure that air tightness is continuous, it's whole, it's unbroken. For this guide in general, when we look at an airtight building, I mean, quote unquote, airtight. What is airtight for one might not be the same as for someone else. In general, we look at a decently performing airtight building is 1 air change, ACH, per hour or better. So anything less than that, we're looking good. Anything more than that, then we're looking at finishing some opportunity to optimize and get better. Now, starting from days gone by, this is how we've always done it. That 2x6 wall, it's familiar. That's the foundation we're starting with here. But we recognize that a 2x6 wall, cavity insulation, can only get us so much R value. It's the way we've always done it, but it has its own limitations. And so there's a lot of different approaches we can do. I mean, going back to this one, if we have a 2x6 wall, start at 2x4 at some point, then went to 2x6, some more insulation. What if we need more? 2x8. There's a pattern here. Let's go 2x10. And we can only go so far. But at some point, we need to look at different options if we need to hit higher performance, higher targets. And this slide kind of shows a lot of those options, because there's a lot of options out there. I'm not here to preach or say that, okay, there's one solution that fits everything. There's a lot of different factors and variables involved as far as material selection, material availability, constructability. There's a lot of things to look at here to see what works and what works for us. And what works for us on this side of the building as opposed to the other side of the building. There's a lot of different things. Today's presentation will focus on basing off that 2x6 stud wall, kind of building from that. Not going too far, there's a lot of options, but we're kind of building from that as a foundation. But recognizing there's a lot of ways to do this, and happy to chat about those as well. So look at the 4 wood framed above walls. The guides provides 4 wall assemblies. And we're going to overview them here quickly, but each guide has a breakdown further of each of these assemblies. But touching base, the first wall assembly is a split wall insulated assembly with a vapor permeable exterior insulation. So that exterior insulation has the ability to breathe. The vapor drive can go through it. Wall number 2, quite similar, also based off of 2x6 stud frame wall, split insulation approach, also vapor permeable, but in this case, it's a wood fiber exterior insulation. So when we talked about carbon, embodied carbon, some options there, this addresses that option. We'll get into it more, but you'll see one detail here shift is that there's now a water resistive barrier on the outside of that moisture sensitive insulation. So we'll dive into that as we get excited and get into that more. Wall number 3, still the same base wall in the sense of the 2x6 split insulation assembly. However, in this one, we pivot on the exterior insulation type. So we're doing a low permeance exterior insulation. So something that has limited ability to breathe, like a XPS or polyiso. And number 4, kind of shifting back to another example we had out in the walls here, is a double stud. So not an exterior insulated assembly, but shifting to that framing to utilize the benefits of understanding that framing, and then tweaking that a bit to make sure we get a higher performance out of that assembly. Disclaimer, so at the end of the day, we're looking at a lot of different wall assemblies, and we recognize that although LEEP provides some great guides, there's a difference between guidance and code compliance. And then sometimes there's a need to have that communication, the collaboration to bring these things in. At the end of the day, the building owners are responsible for that compliance. So it comes down to make sure we hit those targets. But having that awareness and that collaboration with the building official can really smooth out that process. And that's why these documents are great, because it provides the support for the builder, as well as the designer, as well as that awareness for the building officials for them to review that. So when they come to your site and say, this is different, like, it is, but here's why. And it gives you more of that background, that confidence and that context for that assembly. Recognize that some building officials, it's new technology. It's built off of building science principles, things that work, but recognizing that there's sometimes a need to share that information to know where we're building off of. And again, recognizing that collaboration is key. Getting ahead of it before the building permit application process can smooth out that process quite a bit. So that collaboration on all levels is key here. And again, that upfront planning. And then recognizing that there are alternate solutions that sometimes may require an engineer if it's considered too abstract or too foreign. We'll talk more about that code compliance approaches as far as to prescribe solutions, and maybe to require an engineer or a professional. And this is where we talk about it. So there's three approaches: code compliance, prescriptive, letter of the law. This is what they say, do it, match it, we're happy, we're good. No questions, no issues there. A shift from there is at least as well as a like for like, not exactly prescriptive, but the shift that's still acceptable, but add some changes to kind of keep the building officials on their toes. And the third option is potentially, if we go a bit too far out of the comfort zone or the awareness of the building officials, of having an engineered solution that may require stamp drawings or a letter of assurance to kind of provide that confidence that this will perform well. And recognizing that not all of the stuff we're going to present today requires that engineer involvement, but recognizing that communication with the authority having jurisdiction can really smooth out that process. Introduction to this is that first guide. And so here we go. Kind of setting the stage from a building enclosure point of view. As we go through the process, we're going to be looking at the performance of those assemblies, which really comes down to the critical barriers of that assembly. Its ability to do what we want it to do. And so we're all on the same page. We're looking at these 5 assemblies. Starting with the water shedding surface, the water resistive barrier, the air barrier system, the thermal insulation, and the vapor barrier. I mean, there's also things to consider as far as structural and acoustics and fire resistance, but from an enclosure point of view, for that high performance, these are the ones we're looking at. And then specifically for this approach, we're going to be focusing on the air barrier system and the thermal insulation. Recognize that these two, although all 5 are important, these two, if done right, can have a significant impact on that performance of the assembly. So we're going to continue to look at these and come back to this. So kind of keep them back in your mind, take a picture if you want, but we'll be referring to these as we go through the presentation. So the wall assembly 1, here we are. This is that assembly. It's based off that 2x6 frame wall, so kind of your basic thing we're familiar with, having an exterior insulation here. Again, recognizing that this is a vapor permeable exterior insulation, so it has the ability to breathe, but your vapor barriers on the inside being the vapor control layer, your bad insulation, your sheathing membrane, in this case is the air barrier, as well as the water resistive barrier to prevent that protection on the outside of the sheathing, but inbound of the exterior insulation, strapping, cladding. This assembly works out to be about 14 inches, just shy. One thing I want to recognize is we're not presenting, or I'm not presenting this as this is the only thickness of insulation you can get. The guide goes into the ability to change that as needed, to modify that. What kind of R value target are we trying to hit, and kind of ramp it up or ramp it back to fit your needs and your targets. Wall assembly number 2, as we talked about, is that wood fiber exterior insulation. So very similar assembly. We have a vapor poly layer on the inside, your batten frame in cavity. Then we have An air barrier is the sheathing membrane, like your tie bag or such. And then we have your wood fiber ridges insulation. So this is wood fiber, moisture sensitive. So help protect it from that moisture. The approach being presented here is have a sheet membrane on the outside of that wood insulation, help protect that moisture. And we're going to dive into that a bit more, but generally, very similar approach to number 1. Also, in this case, it's about 14 inches. Again, the insulation, exterior insulation can vary, and the guide goes into more of that. Wall assembly number 3. This has the same foundational framing, in a sense, 2x6 wall, cavity insulation, but some significant pivots here. We're adding the exterior insulation, which is low permeability, so an EPS, an XPS, so a limited ability for it to breathe. And that comes with a risk, and we're going to get into it more, is a risk of condensation, potentially moisture that trying to get out, but can't at that point. So here we add a dimple drain sheathing membrane. Something that has some texture and ability for it to drain. So the condensation and moisture that tries to get out can still drain out. And recognizing that vapor control on the outside with the exterior insulation to shift from the vapor poly on the inside as a barrier to maybe a vapor retarding paint or a smart vapor barrier to allow some breathing on the inside. So a teaser there. We're going to dive into that more as we get into that section. But a few key changes here. Also, in this case, it's about a 14-inch wall. Wall number 4, continue with this overview of the different wall assemblies. A significant shift from the previous 3 walls, but the general intent is to capture this as a concept because there's a lot of advantages for the framing style of this. There's some potential risks as far as condensation, things we'll tackle. But in this approach, we still have your 2x4, double stud cavity wall. In this case, we have an air barrier at the back side of that and an interior stud cavity for that service cavity. And this is to protect that air barrier. And we're going to dive more into the pros and cons and how this gets fine-tuned for this reason. A much deeper wall, again, that can vary depending on the wall style and what R value we're looking for, but a deeper wall than the other assemblies. Those are our 4 walls. Yes, I'm excited. We can dive into it. Note that not all walls aren't the same. Pros and cons of both. And the guide, the first material introduction page, it gets into that. It provides some check marks, yellow, light blue, darker blue, and it kind of talks about the qualitative comparison. Yellow being acceptable. And now I say acceptable in the sense of, from an enclosure point of view, as far as durability and performance-wise, not necessarily acceptable from a code compliance. Yes, it'll meet code. Yes, it'll meet the targets, but recognize that what might be acceptable from one might require some communication with the building official to make sure it gets accepted. It is that acceptable alternate solution. The light blue is typically good performance, so not just acceptable, but the next level up. So it's good. It's been well developed, but not quite optimized. And that's where we get the darker blue. Better performance, it's good, and potentially optimized given the different configurations in the category. So in the guide, it breaks these 4 wall assemblies down to 7 categories. Looking at first, the R value versus thickness, the bang for your buck, the effectiveness of that insulation, constructability of that wall assembly, the cost premium, impact of cost, condensation risk for that assembly, moisture management, the ability for that assembly to manage that moisture, air tightness, and adaptability. And we're going to go through some of the check marks for this one. Again, this is just a teaser. There's so much more information that in the guide. We can't capture all of it in a presentation, although I wish we could. I also want to preface that the check marks that are provided are qualitative and not quantitative. So it's not, hey, this one scored a 5.73, or this one scored a 7.2. It's, this one's a bit better, this one's a bit worse. It's more qualitative in showing that comparison. So wall number 1. So we see here that R value thickness and constructability are good. They're doing well. Cost premium, it's noted that there's been a step up in the sense of we're adding exterior insulation, strapping, a bit more to that assembly than what was just a 2x6 wall. So there's some costs associated with that. However, it's also recognizing that for condensation risk, moisture management, air tightness, and adaptability, it's generally optimized. This wall assembly works well to be able to manage those 4 items. And then we compare that to wall number 4, similar cost premium, where we're adding exterior wall assembly, some changes there. Constructability can be a bit tricky, but still doable, but more things to consider because we're adding that exterior water resistant barrier on the outside of that wood fiber insulation. Both recognizing condensation risk is well managed with assembly as well as adaptability, and the other three are still good performing. So it's still a great assembly. Looking at number 3, the highlight here is R value. You have that exterior rigid insulation. Yes, it's low vapor permeance. We have good R value for that, and it's on the outside. It's well positioned. You get a lot of bang for your buck for that performance of that exterior insulation. Recognizing constructability, cost, and condensation, it's acceptable if you manage those risks well. But it's a good performing assembly that still manages moisture well. It's great to achieve airtightness, and there's adaptability in that assembly as well. And then comparing wall number 4, including that in there as well. R value is here where we shift a bit, as well as that condensation risk. Where here it might not perform as well as the other 3, but it still has some benefits as far as constructability. Wood construction, we can bang this up pretty quick, pretty easy, and fill it in. And then the air tightness also has some good benefits here. As we'll dive in, it has not just one air barrier, but 2. And so it has some more confidence in having an airtight assembly. So that was the introduction document. Document 1, in a nutshell, which sets us up and prepares us for the rest of the documents. And we're going to dive into them. This one being assembly number 1, that split wall vapor permeable exterior insulation. And I'll preface it by saying each document is a standalone document. It reads well, it has all the information you need. And I'm going to go through wall assembly number 1, this document here, a bit more depth than the other 3. Just kind of give you a flavor of what's included, what materials in there. And we'll go to the same depth of all 3, but they all have it there. I'm happy to chat about each one on the side as well. So again, looking at that wall assembly, we have vapor permeable exterior insulation. Again, that breathable exterior insulation. And this could be your semi-rigid or rigid stone wool, potentially fiberglass. Our water resistant barrier is that membrane, the sheathing membrane. It's going to be your Tyvek or something that's breathable, because it's both your air barrier as well as your water resistant barrier. And your interior cavity insulation, here's your bad insulation going inside the cavity. And in this case, the vapor control layer is that interior layer, your poly sheet on the inside to stop that vapor from progressing. I throw this slide in here. We're going to talk more about this as we get through the presentation as well. But identifying the difference between low permeance and vapor permeable wall assembly. And we're going to dive specifically into that, but just flagging that this one is a vapor permeable. It's a dryable exterior insulation that has the ability to breathe. And we'll talk more about that from a construction and process of how that comes into play. So it's a teaser for now, like no worry, more information's coming. As great as we're adding exterior insulation on the outside, we still need to attach that cladding somehow. And so the guide knows that we need to do that and provide some support on that. And I want to flag that this is not just information from this looks good on paper, this looks good from a cubicle in a closed office. This is all information that's been built off of the industry. Practice, the assembly is being put into practice, tested by the industry to make sure it works. And to simplify that a bit, it provides a lot of support to both recognize that it can be used for just about any cladding. It goes into light cladding, medium cladding, heavyweight cladding, and what kind of cladding it can support. It also this approach uses long fasteners. So if you ever had a chance to screw through insulation, that fastener can wander. That cause a lot of fun. And this guide provides some support for that approach. But generally it's your exterior insulation, strapping, and a long fastener going through it, attaching back to the wall. In my last presentation, they flagged, last time going through this, they flagged that, hey, that fastener doesn't line up with the stud. And that's correct. So sometimes back in the day, we'd have to make sure we hit that stud to make sure we get the same embedment strength in the pullout. Whereas here, the guide's gone some of the research and looked at, if we have at least a 3/4 inch sheathing, then we don't have to hit that stud. We can have some variability as far as where those screws go to be able to support that cladding on the outside. It does have a caveat here that it's for most cladding, for the typical claddings we have there. When we start looking at like a heavy brick veneer or something that's more substantial, that's now cantilevered away from the wall, that's a lot of weight out there. You can handle up to a certain point, but at a certain point, it needs a little extra secondary support or secondary structural support for that cladding. And there's details that are involved around that, but just recognizing it's still quite capable of handling a lot of the different cladding types we're looking at. A little subtle difference the next click was there's a code compliance icon in the corner there. That's just to recognize, as much as this is a guide, it provides that support, but some things need to be worked out with the manufacturer installation instructions, as well as the authority having jurisdiction, the building inspector. But here's those fastener tables. So it looks at, again, we're looking from a horizontal point of view. In this case, that section view, or the plan view, pardon me, shows the fastener going through the stud. But depending on the cladding type, we can shift that to just be in the sheathing. But it shows it going through the strapping, through the exterior insulation, and into the wall assembly. And this is probably quite small, although your screen's probably a bit bigger. This is an example of a table. It breaks down for different fastener types, what kind of bedment depth we need, what kind of size of fastener we need based on the insulation type and the weight. You can see the three tables of the weight of the different cladding types. So it breaks down a lot of the simple guide. Again, just reiterating, can I use this as my sole resource to know exactly what fasteners I need? Not necessarily, because it hasn't been adopted into the code. But is it a great starting point based on real testing? Absolutely. In-field application? Absolutely. So it's a great place to know how many fasteners we need, what kind of fasteners we need to use it to install this, but recognizing there's still some need, again, that icon, to confirm with the code, confirm with the authority having jurisdiction, your building inspector. And not just leave you high and dry there, the guide also supports you with the exterior insulation assembly. So how we're going to be installing this, whether we're installing it stack by stack, doing like a brick, you kind of work your way up and out, or we're going to use stick pins and do exterior insulation across the whole assembly, come back and then do our strapping, and then come back and do our cladding. It gives some guidance, some support for different approaches. And from my experience, it really depends on the builder. Everybody has their preference and what the crew is good and used to, and what you're used to and familiar with can go a long way. But this helps make that process that much simpler. So the guide is generally a well-rounded support guide to help you through that process. Now, when we look at a wall assembly, it looks great on paper. Sure, everything lines up, it's consistent, it's smooth and easy. And if you look at this wall assembly, there's not a lot of complication to it. We have a wall, we put insulation on it, and it goes up pretty nice. However, as we pivot the corner, we run into more windows, some wall penetrations, a roof, an apron roof. There's a lot of details that suddenly can get things a bit more complicated. And we recognize that we're not all building boxes. I mean, yes, various boxes, but it's not a box with no windows and it's just a shell. There's components, architecture, features, details we want to be able to detail around. And the guide provides support for that as well. In the guide, it provides some examples of mock-ups to kind of show that breakdown of how the different assemblies come together, the sequencing of those approaches. So not just a 2D detail, but some 3D breakdown here. If I had a laser point, I kind of point to the different components, kind of looking from the left to right. Here we see that base of wall, through wall flashing, recognizing some optimization of that, by optimization of these assemblies, mimicked in all three, or the first three at least, the first two, showing that pre-finished metal flashing, not extending all the way through the wall assembly. And we'll go through the details as we get through there, but it shows that improvement of reducing thermal bridging. Another breakdown of the third photo, going from the left to right, of that exterior wall assembly, tying to the roof assembly. We'll go through the details there in a bit. And it's a balcony saddles. Recognize there's a lot of things that tie into. It's not just slapping a wall, his wall works good, but recognize how can we maintain the performance of that wall assembly as we across different details, as we get into different transitions and interfaces. Continuing more, there's not just wall details, but also window installation details. I mean, these are holes in your building that we want to make sure we maintain the best performance we can when punching a hole through that well-performing wall. So how do we detail that properly to flash it, to water drain, make sure we have air barrier continuity, reduce that thermal bridging. So it shows the different components here. And I believe most of these mock-ups we have here, we can get in there, we can look at it, you can see how that sequencing comes to play. But the guides also repeat that and support that process, not just, again, in an architectural drawing or a detail, but in some mock-ups and some examples there. Furthermore, because we recognize for some it's a new approach, this strapping, rain screen strapping, that's not necessarily required all across Canada, because this guide is for all across Canada. There's some places that don't necessarily need the strapping, and it might be new to them. It helps provide some support as far as how do we optimize that strapping positioning. Do I do it every 16 inches on center? Or if I can shift things a bit here, I can catch the jam trim as well as the flashing all on the same strap. So how that support, how to optimize that in your installation. And so it provides some good supportive guidance on that. And there it is, supporting the trim and the cladding all in one. Now we're looking at the exterior installation of flashing. The code language for water management and air barrier doesn't always account for exterior installation. So the wording is still being adapted as far as what's included in the code and what is, trying to set you up for success as far as performance goes. And so when we look at what's code compliant, a flashing tie-in, it might not be in line with what's high performance flashing tie-in. And so as we start varying or straying from what is code compliant or prescriptive, we can still improve that performance, but recognizing there's a need to still have that collaboration so they understand what's going on. So here's an example in this one. If you look at the blue flashing in the middle there, the through-wall flashing comes in and ties underneath the air barrier. So in this case, we have a discontinuity. It breaks. I mean, it's still, water will come down, it'll shut out, but this introduces the potential of not nailing that discontinuity to make sure it's buttoned up. And so the shift here with the guide, in this case, separates the two. So in this case, we have a tieback coming down. It's a water resistant barrier. It is an air barrier, and it's consistent all the way through, continuous. It's doing its job, check. Whereas separately, for the water shedding surface, we have that flashing coming through, and it's tape sealed to the tieback. So we still have continuity. It's still going to go, and the leading edge is protected, but it helps optimize the air barrier continuity for this assembly. And it kind of recognizes that this is a stray from the code. Code compliance is prescriptive, but we still achieve the same targets with this approach. And this is a fun game I like to play with my kids. You know, spot the 10 differences. There's only that one difference. Recognize again that continuity of separating the air barrier to be continuous and separating that water shedding surface to kick out, and kind of making each one is optimizing their different functions. The guide also provides some support as far as calculating the exterior insulation R value. Not just the exterior insulation, but the wall assembly R value. It breaks it down from, you have your exterior, what kind of R value we're getting there, in this case R1, to the interior, that cavity, how much insulation can we get, how much R value can we get from that base system, and the fluctuation of that exterior insulation. 1 inch, 2 inches, 6 inches, how deep can we get to get the R value we need. The guide bases it on approximately R4 per inch, based on a general material type, but recognizing that different manufacturers have different performance data, so something to double check. And in the tables, it provides, if I have this assembly with this thickness, what am I anticipated to get from an R value point of view for that assembly? One thing it also accounts for is potential thermal bridging. So we have this long fastener going through the entire exterior insulation. That's a thermal bridge. Sure. Cold and heat, it's going to be transferred through there, and it'll transfer differently depending on the fastener type. So if it recognizes here that a galvanized screw versus a stainless steel screw will perform differently, and it gives you that supportive granularity of that as well. Now for some of the exciting part. So each guide for each wall assembly has information about the assembly, has a supportive tables, but where I get excited is on these details. So how does this actually come together, these transitions? And so we're going to run through some of these details, recognizing that this is just an overview, and each of the details included has a picture, it has a descriptive, it's got pointers, and we'll walk through it. But we'll talk through some details included in this guide. The first one being an exterior wall assembly that ties into roof assembly. So here we have numbers, we have pointers. What's not shown here is the table that supports all that, so we'll walk through it a bit. This flags the opportunity for that air barrier to be pre-stripped over the wood framing. There's different approaches. You could tie into the wood framing, use that as part of your air barrier. But in this case, by pre-stripping that, we have confidence of continuity of the air barrier. We're tying in. Because on the inside, the air barrier is the interior poly on the underside of the ceiling. And on the exterior, we tie into that tieback. And here, kind of shown by the red lines here, we have continuity from the ceiling out and down, all tied in, and have the confidence that it'll perform really well. And also recognizing that above that, although it might be the same material, it's a different process. It's the water resistant barrier. We have a question here. Yes, sure. So the question here is, are we using a plate poly that goes over top of that top plate to carry that continuity in? It's a yes and a no. So my experience, we don't often use a poly to get through there. Often we'll use like a pre-strip with a tieback or a self-adhered membrane, but it's pre-stripping that. So you build up your wall, and before you put the next part on, next framing on, you just pre-strip that. Now it's tricky for performance-wise. If we're looking at like a tieback, or do we get in the laps? Are we tape sealing those laps before it? And that can do some discontinuity as far as insulation. And we'll get into materials later. Or we're using a self-adhered membrane, so we feel solid, it's continuous, it's going through. But really, yes, pre-stripping that to be able to tie it on the inside and tie it onto the outside. That's a great question. Keep them coming. Keep these questions coming. This is great. Okay. Detail number 2. And again, there's multiple details. We'll go through a sample of them here. This is a through-wall detail, penetration. So whether there's a vent, plumbing pipe, or something going on, we have penetration coming through. Our air barrier here is that exterior air barrier, also our water-resistant barrier. And here it ties in and onto that the penetration, whether it's a vent. One thing flagged here is, yeah, it ties onto it, but how is it tying onto that? There's different ways of doing it with sealant, different ways of doing it with membrane, and that can be tricky as far as make sure we have continuity, we don't have pinholes, make sure it works out well there. One thing we've seen here, well, I believe the guy talks about it, is using an EPDM patch. So it cut a smaller hole. As that pipe comes through, it seals around that and keeps it nice airtight and maintains that continuity. So it's another great approach. Kind of recognizing that we have air barrier, water resistant barrier continuity tighter on that pipe, and then dealing with the water shedding separately to make sure we still maintain that continuity. Here we're showing that through-wall flashing membrane come out, and we're not having that flashing come all the way through. That would be a thermal bridge, reducing the performance of that exterior insulation. And I'm happy to chat about these details on the side. More if we want to dive into it and really talk about different variables of it, but the guide provides a lot of support as far as things to consider in these details. So here we have a window head detail. Air barrier, again, pre-strip that rough opening, get it ready to go so we can tie that window in. Lapping in the rest of the air barrier onto that. So again, continuity, that function, check. Air barrier, water resistant barrier, all continuous. And detailing our water resistant barrier to be able to tie in as well. At the sill, very similar, pre-strip of the air barrier. In this case, it's using a back angle dam to prevent, so this will allow a drainage cavity below the window for any water that gets in there for it to drain out. Having the air barrier pre-stripped in there up to that back angle so we can tie into the sealant, continuous sealant bit around the window into that window frame assembly, and then that air barrier then tying into the rest of it. And the water shedding surface, kind of kicking things out over the exterior insulation. Although the exterior mineral wool has a great ability for it to drain, to breathe, kicking that out helps provide that better, get the moisture out faster. Through-wall flashing at a typical floor line. We've talked about this. Continuous air barrier, let's nail that, make sure that's continuous and solid. And then we adjust the water shedding surface. Also recognizing here that continuity of the thermal barrier, exterior insulation going all the way through, and there's some interior spray foam here as needed. And the base of wall, I recognize, yeah, we have different foundation styles we'll be looking at. In this case, we have your insulated concrete panels, but the air barrier being tied into that panel, tying that into the wall assembly, and then tying the wall exterior air barrier into that. So we have continuity, we have positive shingle lapping, and it's continuous all the way down. In this case, that's both working as the air barrier as well as the water resistant barrier. Each guide is a standalone guide. There's so much material stuffed in there. I mean, it'd be great to say, let's take a day. Let's talk about each guide for the day and have a 7-day conference. Maybe a bit much. Maybe I'm too excited about it. But there's a lot of material in these guides that I hadn't get a chance to cover. We just talked about that alternate strapping approaches, different ways to strap that. It also talks about different flashing attachments. That rain screen free area. So where we have rain screen, where we don't have rain screen, the different pros and cons to that. Looking at the vapor barrier and the exterior insulation, that balance. And Appendix B specifically talks more about that, but having the right configuration is key. More information about the window installation sequencing, isometric details of how that sequence is in there to both provide the designers and the architects and the building officials to know how it works, but also the builders. So if we have a new trade on site, here's some clear guidance of how we're doing it. Oh, someone else is new on site? Let's not start from scratch. Let's keep it the same approach. And then just confirming that the need for air barrier approaches to make sure we hammer that in, it's clear, it's consistent, because that really is what has a significant impact on that high performance assembly. And it also provides some builder's checklists, make our lives easier on site. What are we doing? Have we done it all in process? Check, ready to go. I'll pause there and take a sip of water, see if we have any questions. We had a good question already, but do we have any other questions? Yes, in the back. Oh yeah, there we go. I think there's a mic here, but I can.
I'm curious, do you guys have a chart that compares the R values of these different systems?
Yes. Well, there's the introductory. So the question was, does a comparison of the different R values with these different assemblies? So the answer is yes. The introductory guide shows some comparison between the assemblies, as well as each guide has a different breakdown for the different R values available with that assembly. So if I get 3 inches here versus 4 inches there, how do they compare for that performance? So yeah, a great question, because there's not just one solution that fits all. Which one works best for us for hitting that target that we need to? Great question. Yeah.
Quick question about, I saw in the one detail, wall comes down, it's set back from the front of the foundation so that you insulate out and past it. Is that that's the standard practice on a lot of these?
So the question is the wall is inset on the exterior the foundation. This is here, and there's different ways of doing this. So pros and cons to both. In this case, this is showing that the wall inset a bit, so the exterior, the thermal insulation layer is continuous. So we have continuity. There's not a jag in and out. There's definitely different approaches to this, and there's more details that support that. So if we have the floor extending beyond, how do we wrap that insulation and the barriers around that, or is it just proud a little bit? Again, how to tie into that. So we're not trying to say this is the only way to do it. It can be proud a bit, it can be outbound a bit, it can go both ways. So yeah, there's different pros and cons. I'm happy to chat more about that too, but in general, it's not a fixed solution. There's definitely variability in that, and performance associated with that for sure. The key there is wherever that's positioned, or we have vapor barrier continuity, air barrier continuity, and potentially optimize that thermal barrier for that positioning. But does that answer your question? Okay, awesome. Question in front, yes.
Wall assemblies. On all your wall assemblies, you're all showing 3/4 plywood.
Correct.
I haven't noticed anybody use 3/4 plywood in Lethbridge. It's always, what I've noticed is 3/8 OSB. Very few using 1/2-inch plywood.
Yeah.
So the big thing is that when you're doing buildings, they do building envelope inspections. And so here, when you're doing all that exterior insulation and then you're putting the screws in, you should have, and then the 1x4 strapping, they should have inspection for all the fastening before the before the building envelope goes on. Otherwise, you won't be able to see the fasteners. And so all that cladding weight is just, nobody knows what's holding it.
What's tying behind there? Yeah. So the question is kind of flagging that although our guide flags 3/4-inch plywood, that there's a difference of, are we using OSB? Are we using plywood, but a thinner plywood or thinner OSB? We're looking 3/8, we're looking 1/2-inch. There's definitely some variability. For this guide provides this as an approach. There's definitely approaches as far as how much strength can we get out of those fasteners if we're just going to 1/2-inch insulation, and what support do we need? What cladding can we support on that?
Yeah, you're using acrylic siding, acrylic stucco, or like hardy board, or that's very heavy.
You get a thicker stucco or that hardy board, it can be a lot more weight out there for sure. And recognizing that as much as we have good intentions, there's a need to inspect that. Once that cladding's on, it's all hidden back there.
Well, once the building envelope is on, you can't inspect. Once the building envelope is on, you can't inspect the fasteners. You can't inspect
Yeah.
So how many fasteners they used? So that would have to be, you got to get an engineer involved to say if you're going 16 on center with your screws or whatever the number he comes up with, right?
Yeah, so this is the question, commenting on the need to inspect that. If once we get these cladding and different approach assemblies on there, it's hard to confirm the number of fasteners, the type of fasteners, the spacing on those fasteners, and to have the right inspection done at the right time to make sure it's, is it in place from the inspector side of things? I can't speak to how the inspectors do it. I know if an engineer is involved, like myself, and we're doing part of our field review services, we make sure we come in there, look at a mock-up ideally, early on, make sure, okay, does it work right? Have we done it? Okay, do this, rinse and repeat. As opposed, and then come back again later, do a spot check. Okay, before we get to there's a certain stage where it's still visible, we're making sure we have our things are installed. But I recognize there's a balance between quality assurance provided by an engineer or a registered professional versus quality control that needs to be managed by the general contractor to make sure they're on top of the trade and see what's going on. But that inspection and the confidence of knowing it's installed right is key for sure.
For sure, yeah. So then the engineer would be speccing how you build your wall, whether you use blocking and 3/8 plywood, something similar to when you're hanging cabinets. You've got all your blocking. So either blocking 2 feet on center all the way around the whole building prior to your insulation goes on.
Yeah, so the question is the engineer speccing that? I'd say yes and no. It depends what the coordination of that project is. Is it builder-led or is it design-led? There's pros and cons to both. Are we just make it spec it easy? We have 3/4-inch plywood. You can get a fastener anywhere. You have confidence in that? Oh, pardon me? There's different approaches too. So these guides, I don't want to get too side railed. I'm happy to chat more about it later. But these guides talk about some basic approaches. building off of what's already existing and what's familiar with the industry, and building off those for higher performance. But again, there's definitely multiple ways to approach this with different systems, different air barriers, different claddings, different sheathing types. But you're happy to chat more with that and kind of dive into the different cool options that are available. Yeah. But yeah, there's definitely some cool tools available. So it's fun, for sure. Excellent. Thanks for the question. Okay. Oh, one in the back here. Yes, please.
As compared to ICF, like the pros and cons of this.
That's a great
It seems like
question.
a lot of work just to, like, why not just pour the ICF right to the roof and be done with it?
Yeah, so the question is, what about ICF? ICF compared to from foundation or using it for the entire wall assembly? There's definitely pros and cons to both. This assembly, we're looking at that wood frame approach. You just kind of keep it simple as far as pairing like for like. What's familiar, what's conventional from a 2x6 point of view. Does ICF work? Yes. There's different approaches. Pros and cons again for detailing and transition around windows and top of roof. You definitely still need to maintain your difficult critical barriers. It works. It's not something captured in this guide, but something that the LEEP team told me to do is, if there's interest for more guides specifically made for ICF and how to approach these details, they want that feedback. They want to provide that material that's needed for site and for the industry. So unfortunately, this guide doesn't cover that to that extent. It touches as an option, but definitely it's a suitable approach, and happy to chat with the pros and cons of that on the side as well, for sure. Great flag. It's great to have this group of people that know a lot of different options that are available and the levers we can pull. All right, we're okay. We'll continue on. Spoiler alert, we did wall number 1. We'll jump on wall number 2. Again, I repeated earlier, we won't go into the same depth in this one. We'll kind of touch by the differences, but each document is a standalone document. It goes through all the different information about the wall assemblies. So wall number 2, again, being similar to that first wall, same framing type, except here we have exterior insulation that's wood fiber insulation, so moisture sensitive, something to be aware of. But that assembly from inside to the exterior insulation is the same. The shift being that exterior insulation type, still vapor permeable, still allowed to breathe. And here we have an additional water resistant barrier. So your Tyvek or something that can protect that wood fiber insulation from moisture. Here's an R14 wall, fairly similarly, again, variability in that exterior insulation. Looking at from a bit of a blown out, we have that vapor permeable exterior insulation, wood fiber rigid insulation. The water resistant barrier now separated from when it was air barrier and water resistant barrier in one plane. Now it's moved out, shifting some of the detailing. You need to be able to tie that in properly. Air barrier again being on the back side or on the outside of the exterior sheathing. Again, the air barrier being vapor permeable to allow things to breathe outward. Interior insulation being the cavity, and the same interior vapor barrier being that control layer on the inside. Similar to wall 1, it also provides a support as far as fastener types, support, how much we have the spacing on that based on the cladding types. So very similar, but in this case we have the additional sheathing membrane to protect the wood fiber insulation, WFI. And it has some interesting, some unique air barrier considerations as far as make sure we have continuity of the air barrier with the shift in assembly here. Again, we're just looking at those different critical barriers, make sure it's still continuous as we move them around. Some things to consider about wood fiber insulation. For some, it's new. It's pushing that code. Some building officials might not be familiar with it, so it's a need to kind of collaborate with the building official to make sure it's going to be accepted. And also recognize that not all products are the same. A lot of these things are coming from Europe. They're being introduced into Canada. They work great. They're being tested, but they have limited test data in Canada. As much as it rains over there and it rains here, there's different temperatures, humidity levels. It's a different environment, and we need to recognize that we need to deal with that in Canada by ourselves as well to have some test data here. But the key thing here would be to work with manufacturers and their performance targets in that testing. The test data, the test standard it refers to here is the CAN ULC S706, and not all materials that are coming to Canada have been tested to that standard so far. So they're getting up to speed. They want to present to you with a good product. I'm not trying to endorse one or the another, but they don't all tested the same or yet tested that same. And so recognizing that the code is calling out to have it meet that standard, or if not, look at some alternative solutions that also meet that standard. So here's an example of a few different manufacturers, material types, Sonoclimat, Styco, Gutex, Pavatex. There's a lot of different materials out there, and they have their pros and cons, different R values, different performance qualities, and see what's coming to market. but I'll put a pin in that saying what's coming to market so far. There's a lot more products coming out, and so there's a lot of things available if we want to consider these, embodied carbon approaches as far as what's been included in that, these wood fiber insulation types. When we pull an installation into the code, into these assemblies, the prescriptive approach, what test standards are being called out for different types? Recognize that here again for this wood fiber insulation boards, that this is the code it's calling out for. And not all materials have been tested to that standard. And we'll talk in a minute here about what to look for in those different performance standards. Whereas some materials, wood fiber materials, have been in the industry for a while. So we have an example here of a BP can sheathing membrane. So that is kind of a 2-in-1. It works as your exterior sheathing, but also adds some R value. So also some insulative value, right? And that's an approach that's been around for a while. And it's here we still have it positioned inbound of that air barrier, water resistant barrier. So it's wood fiber, it's still protected. When we shift to this more European approach on the right side of exterior insulation being on the outside, this is why we still need to have that water resistant barrier to protect it. And so we kind of shift the application of that wood fiber approach. So in this case, by protecting both, they're still safe. We reduce that risk. However, if we look at a different type of it, maybe actually hasn't been tested to that same standard, we can dive into the properties. What's the water absorption properties of that material? What's the temperature? I mean, how much R value are we getting for that assembly? What's the water vapor permeability? The ability for it to breathe, and to look at the material. If it doesn't have the same standards, to look at the performance, to be able to look at that critical eye as a potential alternative solution. So we look at this engineered approach. We have that wood fiber insulation. It works. It's great. It needs to be protected. So we have that exterior water resistant barrier. Maybe something new for the industry, so it needs to be stamped or approved by an engineer to have that letter of assurance. Versus the European approach that doesn't have that water resistant barrier. It still could work in some climates. It still could be appropriate. Some of these wood fiber installations still have resin or materials in it that have good water shedding properties to help protect itself from moisture. But kind of highlighting that overall approach of having the right material in the right location, and where needed, protect it as required, which is cover your butt kind of general comment, but it's an awareness. There's a lot of new materials out here, and that are certainly suitable for the industry and certainly great approaches, but to use it as appropriate and reducing the risk where we can. And this guide provides the support for that. Looking at some of the details, again, recognizing that in this case, we have that water resistant barrier outbound, so it shifts. Then we highlight it here. The air barrier is kept on the inside, so similar to other detailing, whereas our water resistant barrier pivots to the outside. Of course, the window, our hole in the wall, works as both, but recognize we need to tie both membranes into that assembly to have continuity top to bottom. And the details go into that more, as well as some blowouts here, some mock-ups that show the different sequencing, the different approaches of both. You see here the tie work of the material outbound of the mineral, the wood fiber insulation. This mock-up being a bit different here for an air barrier. Instead of using an air barrier membrane, they're using the OSB sheathing with tape laps to maintain that continuity. Still, we're still tagging off each critical barrier and make sure we have continuity in the different details. Wall number 3. Again, wall number 2, that guide has all the information that wall number 1 has as well. It's just a lot of repetition, a lot of support, still kept in that standalone document. Wall number 3 here, we pivot a bit in the sense that we have an exterior insulation that's low vapor permeant. That means it has a limited ability for it to dry. So the key things to check out here is that interior vapor barrier, which was near poly, was continuous. We're shifting it to be a vapor retarder paint to allow some breathability. Depending on the temperature, depending on the moisture content in that wall assembly, still allow for the vapor inward to let it dry out. Recognizing that low vapor permeant foam insulation on the outside is a block. It has limited ability for it to dry out based on the insulation type. And so they also had here a dimpled or drained sheathing membrane. And we can talk about the types and different approaches for that. The overview, that low permeance foam insulation on the outside. The water resistant barrier. In this case, potentially being a dimpled or drained membrane, so it has some texture, so any moisture gets back in there, trapped back there, it can still drain out and up, and of course it depends on the details too. The air barrier being that same assembly component. Again, interior insulation, and a shift here with that vapor control being a smart vapor or a vapor retarder paint. Similar to wall 1, it has support as far as faster attachments, cladding types, and that support as far as how to install that. We're recognizing there's a different material, it's a bit more rigid, so there's some nuances as far as utilizing that. And the guide goes into depth on that as far as how to manage that water management and the runoff there. So here we're flagging the differences. So the limiting factor of having that exterior membrane, the exterior insulation, limit dryability. So on the example on the left here, we have a trapped system. So moisture inside the assembly, what typically would be able to dry to the outside through the vapor permeable exterior sheathing, will dry to the outside and dry through the insulation. Here, it's trapped. It would stop there. I think the next one has two walls. So the insulation is a block on one side, that poly on the inside is another block. So how do we get around that? We have some movement on the inside. So it can still dry to the outside, and we can drain it before it gets to that exterior insulation. But if that's not enough, we also have some variability on the inside, so potentially dry to the inside. And the guide breaks this down as far as reducing that risk of condensation and issues potentially with that, with moisture being trapped. And more on this later as we dive into that. But when we talk about that ability for it to drain out, so moisture can be pushed through, the energy going through the wall assembly, pushing that vapor out, hitting the back side of the exterior insulation, low vapor permeance, not ability for it to dry out, it might condensate, collect there, and not be able to support it to drain out. In this case, it could be a grooved or a dimpled sheathing membrane, like a Tyvek drain wrap. It's got that texture. It's got some profile for it to drain out with. It could also be a woven drain mat, a geotextile. So we have air barrier, membrane check. We have a separate material coming in outbound of that provides some drainage cavity. Or alternatively, another solution is having grooved exterior insulation. There's a product you can get that just has a little more texture on the outside. So when moisture does come out, it gets trapped. It still has an avenue or a way of getting out. Similar detailing as far as the membrane, the laps, continuity of the air barrier. One thing they flagged here, it's in the center there, is that with some materials, they don't all have the same profile. And when you have that textured material, it's a textured material. If we try to tape that, it's taped on the surface, but water and air can still get through unless it's done really well. I was on site one time where they tried to use it. They put the sheathing membrane down, and they were rubbing it really hard. They're trying to flatten this sucker out to get a good bond on it. Did it work? Not so much, because it still had that want to have that profile, which created discontinuities that the tape came off and it wasn't working out very well. So here that it's flagging, it's subtle on here, but the guide goes more into it more. They're using a sealant bead. So the sealant, that membrane being pushed into the sealant, it conforms to the different profile of that membrane. Of course, recognizing that the manufacturer will provide installation instructions and support how to maintain the air barrier continuity. The guide also provides these mock-ups showing the different components, how it all ties together, how that drain mat or that ability for it to drain will percolate through. I feel like roll number 3 was faster than the rest of them. There's a lot to go in there. And the guide, again, it goes into it more. I wish we could spend all day on it because it's really cool to see how these things apply and whether this assembly works for you in that situation because you need to optimize it for that certain reason. The guide supports those choices and the pros and cons for that assembly. Looking at wall assembly number 4, this one pivots from the rest of assemblies in the sense of that base framing. We're not looking at 2x6 wall, we're looking at a double stud wall. So my colleague jokes that if you like a stud wall, you like it so much, you build it thrice. And it's because it's got 1, it's got 2, and it's got the interior cavity here as well. Key things we're pointing out here, we mentioned it before, is that interior air barrier. Not all the way into the interior, but inbound between the surface cavity and the rest of the double stud cavity. And this is primarily to position it in a protective zone. So when we're putting up pictures, electrical outlets or plumbing stacks, that can all be positioned with the surface cavity, preventing potential discontinuities in the air barrier and the vapor barrier on the inside. And that's primarily to keep that cavity safe. We'll talk about the reasons in that in a minute. But recognizing that we have the interior surface cavity, that air vapor barrier, that densely packed insulation, and then a vapor permeable sheathing membrane on the outside. But there's not a lot of insulation beyond that to recognize that sheathing will likely remain quite cold in cold climate here. Diving through this fun assembly again, that blown in dense packed insulation between the two wall framing. Different products to use there for sure, but showing the water resistant barrier here, air barrier, but also extra air barrier. Recognizing there's an interior air barrier and an exterior breathable air barrier. That's where we get that optimized air barrier performance. That surface wall insulated cavity on the inside and the protection for that interior air barrier and vapor barrier. and then vapor control layer, again, being that inline, that membrane on the inside, working in both functions. Some fun examples, and we have some examples here as well, whether it's going to be a dense packed cellulose or a different product like that, or whether it's a fiberglass bad insulation, packed in there as well. Different approaches. The key thing for a lot of this is the quality control. Make sure it's installed right. But this assembly does have its risk. When we look at your 2x6 wall or 2x4 wall back in the day, energy would get through that, and if moisture gets in there, it can get through and condensate on the inside of that cold layer. So a deeper assembly means less energy is being pushed through that to dry that out. And effectively, that exterior insulation is still on the outside. It's cold. So there's that risk of condensation. And so back in the day when we had a 2x6 wall, yes, moisture could get in. Yes, it would condensate, and it happens, but it still has the ability to dry out. The energy was enough to push through, push the vapor out, and it could dry. Increase a 2x4 wall or 2x6, 2x8. We're increasing that. It's still a general performance, but a reduced push of the energy going through the assembly. A reduction in that vapor drive will be able to push the condensation out. And as we get thicker still with the double stud wall, we're having more depth, more restriction for the energy to push out and promote that vapor drive. So we increase that risk of condensation on the inside of there. There are ways to approach this to reduce that risk. Not saying it's not going to be there, but just to reduce the risk. And that's having that secondary air barrier behind the service wall. So we have a good air barrier, good confidence that we're not introducing more moisture into that assembly. Properly dense packing the insulation, make sure it's quality control, it's installed well. We're not getting air gaps that might allow thermal continuity through there, conductivity, pardon me, and make sure that it's dense packed and performing well. And then also recognizing there's a source of that moisture on the inside. We can reduce the moisture on the inside to below 40 relative humidity, but also recognizing that we build this and we have our great intentions. We also pass it off to the building owners, and they can do what they want. If there's some communication as far as the risk of these wall assemblies, so they don't put a sauna in there, that can help them as well. But controlling that relative humidity on the inside reduces that risk as well. Pause there for a second. 4 wall assemblies. Each one have their own guide, a lot of information, each one being a standalone guide to provide that support information and pros and cons of each wall assembly type. Because they definitely have their pros and cons, but they're great wall assemblies that are intended to build off of conventional, familiar construction, but has different performance that are intended to meet the different requirements of across Canada. So instead of going to Appendix A, we're going to jump into Appendix B first. And then before that, we'll do a question over here. Yes?
Just looking at making these walls so extra thick, we hit summer and our cold and hot fully switch, right? So is there something taken into account in these guides for the fact that now we have way more insulated value in our vapor barrier all the way back on the cold side through a 16-inch wall? Has that been accounted for or thought about in these guides too?
Yeah, that's a great question. So vapor, the question is, we have this exterior, assembly thick wall. And sure, in the winter it's cold outside and warm inside, and then in the summer, we flip that. Does this wall assembly look at that switch? The answer is yes. It's looked at the different approaches and the different risks of that vapor movement. I mean, it looks at different humidity levels inside and out, the different temperatures inside out, and what's propelling that vapor drive from outside in or inside out. And this guide addresses that as far from not just a performance point of view, but a durability point of view. Because that's the key thing. We have the vapor drive and this moisture potentially collected. Sure, does it perform well thermally? Is it airtight? But how long is it going to perform that way if we have moisture ingress and damage there? And so, yes, the guide kind of goes into that and speaks to the performance of confidence we can have in that wall assembly performing those different climates. Reducing potentially that risk still in that exterior sheathing. Yeah, great question though. Thank you. I think we're doing that. We're okay. Joe, we're still doing okay on time, or? Okay, great. Sometimes we get carried up and talking about this. We'll talk about it all day, but there's only so much time we can fit into a great presentation. So Appendix B, we look at those different approaches with exterior insulation, recognizing the position of that vapor barrier and the depth of exterior insulation we have there plays a factor as far as where's that condensation risk happening. What do we need to do to make sure this wall is acceptable, and in which climate zone is it acceptable? And so the procedure here, it talks through the guide. The appendix goes through the 5 different steps, looking at determining the target R value, calculating the effective R value for that wall assembly, selecting exterior insulation based on permeance. How permeable do we need that exterior insulation to be for that assembly in that location? Calculating the insulation ratio, make sure we have the right balance of where the insulation is within that assembly. And recognizing that we're not just looking at R value, let's pivot and look at all the other components too, your air barrier continuity, your vapor barrier, all the different critical barriers that we need to make sure they're optimized and working well as well. So step 1, determine target R value. There's only so much we can do here. The cold is the cold. It is what it is. We have a wonderful range of climates in Canada, and Alberta's kind of highly there in the middle. But recognizing that the temperature and the conditions we have really dictate with the code, where the targets are required. And that's where we get the targeted R values. Step number 2, calculating the effective R value. You might be familiar with this little breakdown of assembly. The guide provides the support as far as calculating the different layers, different components in that assembly, and also recognizing the limitations of potential R value in a stud assembly and how much exterior insulation we might need to add. Varying it to 6 inches, 4 inches, 2 inches, what's the sweet spot we need to hit that target? Step number 3, talking about that exterior insulation based on permeance, the breathability of that permeable insulation. And here we get a pivot and chat about that difference. At some point, they had to draw a line somewhere. What's permeable insulation? What's non-permeable insulation? And here that line is drawn at 1 US perm, 60 nanograms per pascal per second per meter squared. That's the ability for that insulation to breathe, or a material to breathe. The guide provides some comparison there, recognizing that not all material performs the same. Not only that, but not all material performs the same in the same thickness. So as you differ in material, you differ in depth, you have different vapor permeance. Beyond that, if I can flag a couple here, there's also an order of magnitude different. Yeah, we have green and pink, what's permeable, what's not permeable. But even looking at the green, when we look at wood fiber board, it's got its value. It's permeable, yes, check, it hits that box. But definitely an order of magnitude different when I look at mineral wool insulation. A 9.1 versus an 88.8, significantly different in its ability to breathe and have that vapor drive. But then when you take it down to different thickness, it also changes. So it provides some guidance and support as far as supporting you in picking the insulation that works well for your reduction of risk of that vapor permeance in that assembly. We talked about this earlier, is the risk of potentially trapping moisture. If we have an interior poly barrier, that's our vapor barrier, that's our block. And if we have certain kinds of insulation on the outside, that will also block the vapor drive. So recognize there's a potential risk of trapping moisture. Different approaches in doing this is having that vapor permeable insulation, so it can dry to the outside, or adjusting the ratios. And this is where step number 4 talks about, again, looking at that whole assembly, what insulation type we have where, what's that R value on the exterior versus the R value of the assembly, as the assembly as a whole, and to know what kind of positioning we have with a dew point, or that vapor drive, where the moisture gets in there, where it's going to get cold enough to condense and start causing problems. One comment, kind of pause for a second, is there's code compliant and there's the bare minimum of what needs to be done and what you can do by code, versus what LEEP is presenting here is, let's not be as close to the border as we can, let's have some buffer, some support. So they're aiming to have some higher ratios beyond just code minimum, provide some confidence in their performance. It accounts for potential higher humidity levels inside, and some of those what if scenarios to make sure we have confidence that it's going to perform well in a range of different performance or conditions going to be applied in. So continuing on number 4 here, calculating insulation ratio, going above and beyond those ratios. It looks at different assemblies, so what might be acceptable by code might still have an increased risk of condensation issues, increased risk of limited dryability of that assembly. Whereas if we increase that exterior ratio, so how much exterior insulation we have versus the R value of the whole assembly, we can reduce that risk, knowing that things will be pushed the right way, dry out the right way, and condense in a safe spot. So as we get thicker here, we see that risk being reduced based on those higher ratios. The guide provides a lot of breakdown between different climate zones, different ratios. There are targets for that, again, being a bit more above code. And it also talks about the different humidity levels inside as well. So it really gives the granularity, some support for you to find out what ratio we need, how well is that assembly going to perform. And then step number 5, bringing it back to some of the basics. Yeah, we looked at R value, the thermal barrier, but also consider vapor control. Also consider air flow control, water management, cladding attachment. Kind of brings it all back to make sure we're not forgetting one of the different components and potentially increasing one thing, but maybe reducing something else. And not just give you some guidance here. Good luck. Have some guidance. It gives some examples, some wall assemblies that how would this work in this climate. So we'll run through some of those examples as a case study. Here we're looking at wall example 1, an R19 bat in a 2x6 wall assembly. Again, an interior vapor barrier. In this case, it's a mineral wool insulation, R8, for about 2 inches on the outside, and the air barrier being a vapor permeable air barrier, so it allows it to dry to the outside. So kind of run through the checklist. We've gone through our ratios. Is a ratio required here? No, we're not worried about trapped moisture of the ratio because it's a vapor permeable exterior insulation. It can dry to the outside. We're happy there. What's the ratio of that insulation? About a third, 0.31. That's the portion of insulation on the outside versus the whole assembly as a whole. Where is this appropriate? Anywhere. This assembly works as far as we're meeting those R value targets for what's required in those locations, but it's not restricted for climate zones for that risk. And then some additional notes it provides is, that permeable insulation allows for that standard practice for efficiency and boost R value, so it allows that flow of insulation. Whereas I pivot here a bit, looking at a different assembly. So still 2x6 wall, a bit more R value in that bat, so they're improving the cavity insulation. And they've also added a smart vapor barrier on the inside. But that exterior insulation is polyphase EPS, low vapor permeance, limited ability for it to dry. So are the ratios required? Yes, flag. Exterior insulation is vapor permeable, ability for it to trap moisture, so you gotta be mindful of this ratio. What is that ratio? Outboard to total R value ratio, 0.26. Looking at exterior insulation versus the cavity as a whole. Where is it appropriate? Well, up to climate zone 5. Up to that level of coldness, this can still be suitable based on the vapor drive and the exterior environments. And this is effectively an R value of R26. Key things to note here, interior vapor retarder is key to using this wall because it still allows the ability for it to dry to the inside. So we're not trapping the moisture between the two. Another example, here they try to keep us on our toes. We're not splitting insulation halfway through, it's trying to show both types. But looking at insulation ratios, yes, is it required? Because in this case, there's no interior vapor retarder. So if we want to do an assembly that doesn't have an interior poly, doesn't have an interior control, do we need to worry about the ratios? Absolutely, it's a key trigger. In this assembly, we're looking at R12 bat, so not a lot on the inside, but a significant amount of insulation on the exterior. R25 with that 7 inches of wood fiber insulation, or they're using the XPS as well. So having the bulk of the insulation outbound. How much insulation is out there? When we look at the ratio calculations, again, it'll walk us through that process. Calculating outside versus in, 0.66. So we're looking at 2/3. The majority and then some of that insulation is outbound. Where is it appropriate as far as climate zones? Design climate zones C or 7B for your standard interior REH. If we have a higher interior relative humidity, there's some things to be considered, and it gives guidance on that. But this is an unusual assembly in the sense there's no interior vapor barrier. And we actually flag that because it can work well, it can be high performance, it can be suitable for a range of climate zones, but just highlighting that need to collaborate with your building official or inspector. If you build this wall perfect, it looks great, and they come in and they just stop dead in the tracks, there's no poly. You're done. Whoa, we don't need poly, and here's why. So having the supportive guidance and to understand why there's not a need, why we've reduced the risk, and how this assembly works in all those different climate zones. Flagging here again, that's R36.4 wall, depending on insulation types and performance qualities of that insulation. And the additional notes here, the high ratio is needed in order to remove that interior vapor barrier. If we're going to remove that, we need to have significant amount of exterior insulation there so we can control that vapor drive and where that condensation will be, potentially could occur. And another example, kind of balance things out. Our ratios required. Yes, in this case we have exterior low permeance insulation, so again, limited ability for it to dry. With a 2x6, 2x8 wall with your interior poly barrier. What's the ratio? 0.18. So some insulation on the outside, sure. Majority of it's on the cavity wall. Is it recommended? It's not recommended. Nope. Like the eyebrows, nope. I don't think so. Primarily because of the risk of condensation within that wall assembly. Here we have a risk of it trapping moisture. Could it be prescriptively acceptable by code? Potentially. That's where you need to be careful of that risk of where that condensation is going to be, and working with this guide to provide that confidence of how much insulation where, and be able to make sure we have that vapor movement and drainability if needed. So a good flag, good example. Whew, that was just like a teaser. There's so much more in there as far as that balance of exterior insulation versus what's to find the right material type for the low permeance insulation. And there's more information there, so dive into it. Happy to chat more about it as well and to go through the information, but let me know. Appendix A, here we have some fun with material selections, unless we have any questions. I think we're just excited to jump into material selections, aren't we? Okay, so Appendix A, material selection. What does this include? Well, it includes material selection basics. What material are we looking at? Is the materials code compliant? Is it durable? Is it fit for construction? Is it compatible? Compatibility between different material types. Adhesive natures of these materials, the constructability of the materials, construction grade. Is it suitable for construction, or is it just, it says it'll do it, but it doesn't actually perform the test of time? And I want to again comment here that we're not doing this one solution fits all. It's probably a range of solution of products that again are not based on someone in a cubicle looking at product data sheets. It's stuff that's been tested in the field, it's been proven in the industry, that works time and time again. Does it capture everything that is on the market or will come to market? It's growing, but it's definitely a great resource for utilizing there. It talks about sheathing membranes, and I flag this that we're not endorsed by a certain material. They're not saying, hey, promote our stuff. It's just taking it unbiased, looking at performance and what's suitable. But it talks about different sheathing membranes, the suitability of those, different flashing membranes and tapes, adhesions and transitions, different insulation types, ones that we can depend upon for good constructability and usage on the field, different sealants, because not all sealants perform well, and having the right sealant in the right location is key. It also talks about that consumer grade versus construction grade. My colleague put together the slides here and had some Flex Seal tape, and I'm all about Flex Seal, it's fun. But looking at, you go to Walmart and there's a wall of sealant. My kids usually leaving at that point go to the paint section and pick up little swatches to make crafts out of, but there's a lot of sealant to choose from. And knowing what is 100%, because it says it's 100% waterproof, whereas what is really 100% in testing, in construction, in adaptability. And so the guide provides some support and guidance on that as far as getting past the 100% waterproof or the crack proof, superior flexibility, silicone tough. I mean, the slogans kind of speak for themselves. Sometimes if they promise too much, they might underperform. I don't have pros and cons either one, but there's a need to make sure you're looking at the good products, which I'm sure you're all familiar with, but this gives some support as far as products you might be familiar with, as well as products that you can have confidence in, because others will stand behind it as well. But as much as we can select the right material, good material is only as good as the application. So we look at an install like this, things are looking great. We did a nice mock-up. Things are well rolled, adhesion's good, laps are great, things are tape sealed. We're looking happy. We have confidence that material is going to serve for its intended purpose. However, we pivot and we do a drive-by and we're like, yeah, maybe potentially a lack of confidence in continuity there, especially when I can see distinctly that is continuity. So the install is key, which pushes mock-ups, which pushes testing things out, but the installation can only go so far with the right material. So I'll pivot there and look at, we've talked about a lot of different components here. First being the introduction guide, the 4 wall guides, the supportive appendices, and that is all good for new construction, but it's also applicable for existing buildings as well. And this we'll talk quickly about the retrofits. Here's some examples of, again, looking at retrofits. When we look at all the different critical barriers, key things to consider here are better air tightness, better R value. That has the big impact on the performance of assembly. And if we look at your typical 2x6 or 2x4 stud wall framing, are we going to add stuff to the inside or add stuff to the outside? What are the risks involved with that? Again, building off the same principles we had in the previous sections. So new interior insulation we have the hygrothermal risks, the risks of water and air and heat, the different components of that. Whereas adding exterior insulation, there's less risks. You can still run some problems with the wrong material, but to be aware of. Yes? So hygrothermal is that movement of moisture and heat through assembly. So that the combination of them that can cause that condensation issues and stuff like that. So great question. What is hygrothermal? It can be a fun tongue twister, and not everybody's familiar with it, but it's building enclosure, fun stuff. Here we chat about those wall assemblies. Again, recognize that we take in a base wall, we're changing it. What's that exterior insulation doing? Is it staying cold and we're reducing the energy flow through that assembly and the ability for it to dry? So again, it's cold. It's still cold. Increased risk for condensation. Colder still, increased risk of insulation. So being aware of the ability for it to dry out. So one approach to that is keep the insulation warm by your base assembly. Sure, let's add some insulation to the exterior. Add a bit more exterior insulation, and we can see how that insulation, that sheathing layer, becomes warmer and warmer, reducing the risk of condensation occurring at that location. Whereas with an interior assembly, it's cold. We got some insulation the inside. The exterior layer is still cold. So having the interior surface cavity to prevent any moisture from getting in there, which reduces that risk of condensation. So we can still get in there, so reducing that risk. Having an excellent interior air barrier reduces the moisture getting in. Actually balancing not just the assembly, but also the ventilation inside, reducing the moisture potentially in that assembly. And then trying to update it so we have permeable exterior insulation and permeable rain screen assembly. And sometimes when you can't improve it and you're just stuck, it's going to get wet, we can reduce that risk by potentially doing a biocide treatment or kind of treating the material so it's more resilient against that moisture that might penetrate inside there. Looking at all the 4 wall assemblies, it's pretty cut and dry. The first 3 are exterior insulation approaches that can be applied for retrofits, versus rule number 4 is more of an interior retrofit approach. So this kind of takes that cut and dry, the gray being what's existing, and adding the exterior or interior insulation here. Again, looking at those same 5 barriers, if we're looking at the same 5 and see how they might move with an interior approach, water-saving surface, water-resistant barrier, generally stay in the same position, whereas we're moving the insulation inward, new vapor barrier, new air barrier by adding it in there to add the compliance, shifts the performance of that assembly. Other things to consider on the interior air barrier approach is, planning for the joists, the floor joist areas. I mean, how are these things moving in and out? Can we reposition the interior surfaces so we have that continuity of the air barrier? And then also recognizing we're going to have some things we have to work around. Bringing that wall in, we're going to have to deal with stairs, tubs, cabinets, counters. There's a lot of things we have to do detail around. It's simple to frame around that, but also recognizing we want to have air barrier continuity around all that as well. Lots of free framing, which is fun. If done unwell or less well, there can run into problems. And we've been a number of projects we've been involved with where you see that sheathing being decayed. If you have moisture gets trapped in there because they haven't looked at it holistically. We'll just slap more insulation on there. It'll be fine. It'll change the performance of the window or the assembly, so something to be mindful of. Just kind of flagging that interior surface cavity. Yes, we put that in there. It helps protect the air barrier, but if we need more R value, we can still beef it up a bit more, having more interior insulation. If we're looking at exterior assembly, we're putting more exterior insulation on the outside. How does that affect the assemblies? So a lot of things stay in the same position, and really the insulation moves out, and the water-saving surface moves out. It gives us an opportunity to maintain that air barrier and new water resistant barrier continuity, kind of improving that material type and the continuity there. Things to consider are the components we're working around. Now we're going around balconies, we're going around different components, canopies, roof and garage interfaces, as well as those exterior penetrations, a hose bib. There's things to work around, things to detail. The key thing is here to make sure we maintain our air barrier continuity and the different components there. So we need to reposition the window to move it out so it's in line with the thermal barrier. So a lot of things to consider to chat about there. Happy to chat about those tie-ins and information as well. So we'll flash through some of these components, different assembly types. Take your typical roof wall assembly, adding exterior insulation. In this case, we're shifting that air barrier to the sheathing, adding insulation up onto that, and maintain that continuity. Kind of shows the example of maintaining that water-saving surface as well as drainability. Base of wall retrofits, showing that the continuity of the air barrier coming down. Sure, we've done a retrofit, but make sure we still tie in the air barrier into the foundation, and potentially adding some interior insulation as well to make sure we manage our R value or condensation risk. Detailing around balconies, so we're adding more exterior insulation, but make sure we have continuity across that and not reducing that with thermal bridging. Here's some fun examples where they've done this. They have a 2x4 wall, added exterior insulation to it. They've beefed up that wall, but they've improved the vapor barrier, improved the air barrier with a self-adhered membrane, added exterior insulation, moved the window out so it's in line with the thermal, so we have a good thermal layer continuity here. Here's another example of a 1956 bungalow where they did the same. They stripped all the cladding off, redid the roof. So a nice new metal roof, adding exterior insulation, improving the air barrier. And at the end of the day, still looks pretty great. They actually had a chance to reuse some of the cladding there to repurpose it and maintain some of the similar look, but significantly higher performance from what was there before to what they have now, and considerably more comfortable living space as well. There's a lot of different approaches. Some things to consider: the Larson's truss approach, as far as getting more insulation into that assembly. So with the surface cavity, one other approach would be the insulated panels. There's definitely a lot of prefabricated solutions to this as well. But again, looking back at all the different critical barriers to make sure we maintain that as considerations. One flag of warning from a sustainable point of view is use of spray foam insulation. My dad always said, right tool for the right job. Spray foam is great in the right location, but recognizing it's not sustainable, you put it in there, you can't take it off, reform it, and put it back. It's one and done. So from a sustainability point of view, as well as like embodied carbon, there's things to consider, as well as risk of limited dryability. We have some good examples here of good application, and let's just say less good application. Different material types, continuities. You see at the bottom right, it's my job is the Tyvek, his job is the spray foam, and when they don't meet, we potentially have an issue here. But also recognizing the quality in the top center, it can, from a quick drive-by, it can look like it's continuous, but if not done well, we have air holes, gaps, and that can cause problems because, like Jurassic Park, life will find a way, water will find a way. It'll get in there. I think we have some examples here of that happening. Well, the next one's examples. This is just that application. Make sure it's done well. Control quality, have a good trade to do that is key. When it's not done well, we can see how it can work as a wonderful sponge. Water will get in there, it'll collect. It can often be hidden, and so we don't know about it. And it's one thing if it's trapped in the insulation, but if the insulation is trapped against wood, the moisture is being held into that wood, can cause some serious problems pretty quick. So, not to scare you away from closed-cell spray foam, just word to the wise, make sure it's installed right. Be aware of moisture ingress. Some go-no-goes. Generally, I'll run through this pretty quick, but interior and exterior are pretty similar. Air barrier continuity, top priority. Make sure it is airtight to get that improvement we want. And it requires quality control, quality assurance to make sure that it's done well, and having improved ventilation. Things to watch out for is, are we adding new insulation without talking about the air barrier? So we're improving the performance-ish, but are we creating potential problems by having air leakage through that assembly? So we recognize they go hand in hand. Looking at the exterior, very similar. Again, looking at the things we're adding to make sure we're looking at holistically how the wall is going to change. And these guides give them that conversation about how things are going to perform and work together. There's a QR code in case you missed it, but in snapshot, there's the 7 guides. There's a lot of material here. Only covered the tip of it, but the intro guide helps you select which wall guide works best for you. The 4 wall guides help you know what the pros and cons of that wall guide work for you, and you could be able to compare the difference. And then material selection support and exterior insulation selection support as well. Which brings us to the end. A lot of fun. Thank you very much for your questions, your involvement. I'm not sure if there's any more final questions, but as a side note, I'll be available on the side. I'll be here all day, so come grab me if you have any questions. I think I probably ran over time, but we'll turn time over to Joe for some more fun.